Video Lecture 10A, Hybridization and Valence Shell Electron Pair Repulsion, or VSEPR. In lecture, we discussed valence bond theory for very simple diatomic molecules. Remember that valence bond theory requires that orbitals overlap to form covalent bonds. We can describe two types of overlap: sigma overlap and pi overlap, depending on the direction in which the orbitals are pointing when they undergo this overlap. However, for polyatomic molecules, we need to consider one additional factor, and that's three-dimensional geometry. When three or more atoms combine to form molecules, molecular geometry is important for energetic reasons. Therefore, our valence bond model needs to consider this when describing the overlap. The three-dimensional geometry of our bonds depends mainly on the orientation of the orbitals when they undergo the overlap. If we look at our atomic orbitals, we see two main types: the spherical types, which mainly describe the s orbitals, and then our d, p, and f orbitals. The d, p, and f orbitals tend to be orthogonal to one another. This means that their lobes have 90-degree angles between them. Here are on the right are some pictures of the 2s and 2p orbitals. You can overlap with an s orbital and generally in any direction. For the p orbitals, the lobes point at 90-degree angles from one another. However, this poses a problem. Most molecules do not have 90-degree bond angles. Therefore, we need to rearrange our orbitals so that they give us the correct molecular geometries. Linus Pauling came up with a solution to this problem, and that is hybridization. The hybridization of orbitals is nothing more than a mathematical calculation. To hybridize orbitals, we take linear combinations of atomic orbitals that are on the same atomic center. Taking a linear combination simply means that we add and subtract their wave functions. You will not be responsible for the mathematics that goes along with hybridization, but we will look at their effects. When we take linear combinations of atomic orbitals to get our hybrid orbitals, those orbitals will have approximately the same shape, except they will now point in different directions. For example, if I take a 2s orbital and a 2p orbital that are on the same atom and I hybridize them, I will form a hybrid orbital. Notice that the hybrid orbital has a different shape than the 2s and the 2p orbitals. There's one very large lobe and one very small lobe. The larger lobe is typically what participates in bonding, since its electron density allows for more efficient overlap. Whenever you form hybrid orbitals, they must be the same in number as the types of as the orbitals you start with. For example, since I am taking a 2s and a 2p orbital and hybridizing them, I should expect to get two sp hybrid orbitals, one pointing in one direction and the other pointing in the exact opposite direction. This comes from taking two possible linear combinations. We name hybrid orbitals from their parents. For example, in our example on the right side of the screen, since we are adding a 2s and a 2p orbital, we get an sp hybrid orbital. Again, we make these hybrid orbitals to get orbitals that reproduce molecular geometries we know from experimental measurements. It's a happy quirk that our linear combinations give those same geometries. We'll now use our hybrid orbitals to look at a valence bond theory description of methane. Here's the Lewis structure for methane, CH4. Note that carbon is forming 4 single bonds with 4 hydrogen atoms. This will correspond to 4 sigma bonds. If you look at the Lewis structure for methane, you would think that methane is a flat molecule with bond angles of 90 degrees. However, from experimental measurements of the methane molecule, we know that methane is indeed not a flat molecule. It has a tetrahedral shape. The carbon-hydrogen bonds are pointing at the vertices of a perfect tetrahedron. This predicts bond angles of 109.5 degrees. In order to reproduce these bond angles, we must employ hybridization. To do this, we combine the 2s and all 3 2p orbitals of carbon to form 4 sp3 hybrid orbitals. Here's a pictorial representation of what we want to do. Here's a carbon atom, represented by the black dot in the center, and all of its valence orbitals, the spherical 2s orbital and the 3 2p orbitals, all pointing at 90 degrees from one another. Below the picture is the orbital occupation diagram for carbon. It has 2 electrons in its 2s subshell and 2 electrons in its 2p subshell. We will now take our linear combinations. It is not important that you understand the linear combinations. You just need to know the result. Once we finish our mathematical tricks, we'll end up with 4 equivalent sp3 hybrid orbitals, each occupied with 1 electron. Note that the new orbitals are pointing in different directions than their original atomic orbitals. The mathematics of our hybridization results in 109.5 degree angles between the lobes of the orbitals. In our picture of the hybrid orbitals, we're leaving out the small tail, but remember that all the hybrid orbitals kind of look like whales. 1 big lobe, 1 small lobe. The big lobe being the body of the whale, while the little lobe is the tail. We now have orbitals that point in the proper directions to reproduce the bond angles in our methane molecule. Now we're ready to do our orbital overlap. The sp3 orbitals are ready to overlap with the 1s orbitals from hydrogen because they're singly occupied. Note the picture on the right, which shows all of the orbital overlap. The orbital overlap occurs between the sp3 hybrid orbital from carbon and the 1s orbital from hydrogen. This happens 4 times to produce 4 equivalent carbon-hydrogen bonds. Note that the little electron pair that is in the overlap region is simply there to remind you that the overlap represents the sharing of 2 electrons. These are all sigma bonds because the 1s orbital from hydrogen and the hybrid orbital from carbon are overlapping directly, not sideways, as what occurs in a pi bond. You may wonder, is there an easy way to predict hybridization besides doing complicated mathematics? There is. And this is where the valence shell electron pair repulsion theory comes in. known as VSEPR or VSEPR theory for short. This theory was described independently by Gillespie, right around the time Pauling came up with valence bond theory. VSEPR theory gives a physical explanation as to why we need to hybridize atomic orbitals, and it's a very simple one. VSEPR theory says that signal bonds in lone pairs will orient themselves to minimize electron repulsion. Since electrons have the same charge, they will repel one another, and if they're close to one another, this will raise the potential energy. Therefore, they move away from each other to minimize their potential energy. Here's an example. If I have 3 electron pairs represented by the 3 blue balloons, they will move away from one another to adopt a trigonal planar geometry. That means that they will have 120-degree angles between them. This will put the structure at its energetic minimum. We can easily use VSEPR theory to predict the hybridization of an atomic center that's surrounded by 2 or more electron pairs. These electron pairs could be sigma bonding pairs or lone pairs. Notice that we do not explicitly treat multiple bonds, such as double and triple bonds. We're only concerned about the sigma bonds and the lone pairs, since these directly impact the geometry around an atomic center. Here are the 3 most common orbital hybridizations. You'll be asked to memorize them. If there are 2 electron pairs around an atom, typically both bonding, the atom is said to be sp hybridized. The hybrid orbitals will have a linear geometry with an angle of 180 degrees between them. This angle puts both electron pairs as far apart as possible. If you have 3 electron pairs around an atomic center, the atomic center will have sp2 hybridized orbitals. These hybrid orbitals will adopt a trigonal planar geometry with angles of 120 degrees between the lobes. Again, these angles keep the lobes as far apart as possible. The last common hybridization deals with 4 electron pairs around it, just like our methane example. The hybridization is called sp3. These sp3 hybrid orbitals will adopt a tetrahedral geometry. The angle between all of the lobes of the orbitals will be 109.5 degrees. Once again, this keeps all of the electron pairs as far apart as possible. These are the 3 most common orbital hybridizations, and you'll be asked to memorize them. The last 2 are not as common in general chemistry courses, so you won't be required to memorize them. However, we will still take a look at them. If there happens to be 5 electron pairs around an atom, we will need to involve d orbitals in our hybridization. To accommodate 5 electron pairs, we will need to have sp3d hybrid orbitals. These orbitals will adopt a trigonal bipyramidal geometry. In the vertical or axial positions, the bond angles are 90 degrees from one another, while in the planar region, the lobes are all 120 degrees from one another. The geometry looks like 2 pyramids with a triangular base stacked one on top of another. The last possible orbital hybridization accommodates 6 electron pairs. This requires sp3d2 hybridization, or it requires us to mix 3p orbitals, an s orbital, and 2d orbitals. The resulting hybrid orbitals will adopt an octahedral geometry. All of the angles are 90 degrees from one another. In the following example, we will use valence bond theory and VSEPR to describe the bonding in formaldehyde, whose Lewis structure appears on the right-hand side of the screen. We're going to use valence bond theory to describe the bonding in formaldehyde, which is CH2O. The Lewis structure is provided for us right here. Now we're only concerned about the carbon atom since it is bonded to more than 2 atoms. We notice that there are 2 single bonds from the carbon to each hydrogen atom. Each single bond will be formed by 1 sigma bond. Carbon also forms a double bond with oxygen. We know that double bonds are formed when a sigma bond and a pi bond is formed between 2 atoms. Carbon also has no lone pairs on it. Therefore, we need an orbital geometry that is able to describe 3 sigma bonds. We will also need to describe the 1 pi bond that forms between carbon and oxygen. According to VSEPR theory, in order for 3 bonding pairs or 3 electron pairs to have a minimum energy geometry that keeps the electron pairs as far apart as possible, this will require a trigonal planar geometry. Trigonal planar geometry will require sp2 hybrid orbitals. We will now represent this in an orbital overlap picture. We start by placing a carbon atom in the center. These dashed lines represent the orientation of the sp2 hybrid orbitals. Notice the trigonal planar geometry. The angles between the orbitals will be 120 degrees. We will now draw our 3 sp2 hybrid orbitals. And label them. Now it's time to represent our orbital overlap regions. Let's begin with the oxygen. Oxygen has 2 unpaired electrons, each in 2p orbitals. Therefore, one of oxygen's 2p orbitals will overlap with one of carbon's sp2 hybrid orbitals. Again, we want to label our orbitals. This is an oxygen 2p orbital overlapping with an sp2 orbital from carbon. We also want to label the sigma overlap region. You can even put a pair of electrons there to remind you that that's an electron pair. We now need to show the overlap between the sp2 hybrid orbitals and the 1s orbital from each oxygen atom, or from each hydrogen atom. Again, we should label our 1s orbitals. We should also label each sigma overlap region. Again, you can put a pair of electrons there to remind you that this represents an electron sharing domain. We have now represented all of the sigma bonding that takes place in formaldehyde. There are three sigma bonds, one between oxygen's 2p orbital and an sp2 hybrid orbital from carbon, and two sigma bonds between the sp2 hybrid orbital from carbon and a 1s atomic orbital from hydrogen. We now need to describe the 1 pi bond that's in formaldehyde. We can do that as follows. We first need to represent the sigma framework. We can do that by drawing our carbon-oxygen bond in the horizontal axis. We can represent the hydrogens by using dashed wedge notation. The dashed line means that this carbon-hydrogen bond is going behind the plane of the whiteboard. The wedge line represents the hydrogen atom that's coming out of the plane of the whiteboard. Essentially, we're taking our sigma framework represented here and rotating it about 90 degrees. Now we can show the overlap between the two unhybridized 2p orbitals, one on oxygen and one on carbon. These two orbitals overlap sideways to form a pi bond. Remember that pi bonds have two areas of orbital overlap, one above and below the bonding axis. This represents the sharing of two pairs of electrons, which you can represent by two large arrows. We have now fully described the bonding in formaldehyde using valence bond theory.